Hi there, I'm Borna, your organic chemistry tutor, and I'm back with another solve mechanism problem. Let's get started on it. For today, I have this mechanism problem for you. It may look a little intimidating on the surface, but I promise it's not that bad. You should be able to try this mechanism if you have learned the alcohols chapter. So I give you a few minutes, pause the video, go ahead and try it, and then come back. Alright, so let's work through the solution. Looking at the structure of the starting material, first of all, one thing jumps out at me, and that's the fact that this thing doesn't appear anywhere in the product. And it's a very stable base, very weak base, meaning that it's a very good leaving group. So I'm going to say it's more likely than not just a good leaving group and doesn't do anything apart from that. So I'm going to make this leave. And for solving this mechanism problem, I'm going to go through two strategies at the same time. I'm going to think about what makes sense, and then I'm going to try to see what carbons am I supposed to connect to what carbons based on numbering the carbons in the starting material and the product. And if I'm wrong in terms of numbering, that's always fine. I can go back and change that. No problem with that. Okay, I'm going to start here. 1, 2, 3, 4, 5, 6, 7. Notice that I didn't number the carbons that are like the methyl substituents on carbon 7 and carbon 3, and that is because we have a dimethyl present in the product and a methyl present in the product as well. And for right now, I'm going to assume that the one that has the dimethyl is 7, the one that has the methyl is 3. Now, this is not to say that the methyls cannot shift, but let's go with the assumption that they didn't. And if it turns out that it doesn't make sense, then we'll do something about it. Now, in the starting material, 3 is connected to 7 by 4, 5, 6. And I'm thinking, what if 4, 5, and 6 were these? Well, maybe that is wrong again. I mean, like, we never know. But we'll start like this, and then we'll worry about it later. Also, it turns out that 3 is connected to 2 and 1, so there's no reason for the bond between 3 and 2 to be broken. So I'm going to say that this is probably 2, this is probably 1. And with that being said, well, obviously the bonds that are being broken, I'm going to show broken with red, and I'm going to show made with green. So obviously the bonds that are being broken are the bond between the carbon and the thing that we decided is the leaving group. Let's see what else. 3 is being connected to 7. Okay, so 3 is being connected to 7. What else? I can see that. Well, 2 was connected to 3. Well, no problem there. 3 was not connected to 7. It got connected later on. Oh, 1 also was not connected to 6. It got connected later on. And I cannot locate any other bond that was made throughout the course of this process. Now, let me go ahead and translate my numbering to my first carbocation that I generated. So I have 1, 2, 3, 4, 5, 6, and 7. All right. 1 is positive, and note that 1 and 6, according to our analysis, are supposed to get connected, and 6 is a part of a double bond. So what if I went ahead and used the electrons of the double bond to create a ring with 1? Now, what did that look like? I'm creating a 1, 2, 3, 4, 5, 6-membered ring, so I'm going to draw a 6-membered ring. I'm going to number that with red. So I have 1, 2, 3, 4, 5, and 6. And then on carbon number 3, I have a methyl, so let's go ahead and put it in place. Between 2 and 3, I have a double bond. Nothing happens to that. On 6, I'm going to have an isopropyl, and then 7 is going to be connected to 6 with a positive charge. This is actually looking very good, because now I have a positive charge on carbon 7, which is this. Let me actually demonstrate that. So carbon 7 is this, and carbon 6 is this. Let me just be very clear about that. And 3 now has an opportunity to get connected to 7 because 7 has a positive charge on it, and then 3 is a part of a double bond. So I'm going to use the electrons of the double bond to connect that or create that bond, and that'll lead to a structure, a bicyclic structure, where I'm going to have a dimethyl bridgehead like this. I'm going to have, say, I'm going to put 3 right here. So I have 3 right here, I have 2 right here, I have 1 right here, I have 6 right here, I have 7 right here, I have 4 and 5 right here. Give it a few seconds, let's see if you can basically see what is what in this structure, and don't forget that 2 has a positive charge. Alright, I hope you can make sense of this. And now looking at this, this is very close to the structure of the product. It's just like flipped, it's just rotated, which is perfectly fine. And all that needs to happen now for me to get the product is that this carbocation needs to be intercepted by a water molecule and basically form an alcohol. And due to the steric hindrance of this dimethyl bridge, the attack apparently takes place more predominantly from the bottom face of this ring. And I get my OH down here, and then all that needs to happen now is that another molecule of water has to come in and abstract this hydrogen. And then I have the product. So let me just recap. Here is what I did. I thought about what made sense to happen, and what made sense to happen was to first lose this entire circle thing as the leaving group, create an initial carbocation, but that proved to be a little confusing. So at that point, I went ahead and numbered the carbons and tried to locate those carbons within the product and decided what connections needed to be made. And based on the kind of connections that needed to be made, I was able to basically see where to get from this, how to get from this carbocation to my desired product. That wasn't that difficult, was it? I hope you liked this video. If you did, please don't forget to hit the like button and share this video. That's going to help me tremendously. Also consider subscribing to this channel for more tutorials, solved problems, and tips and tricks. See you in the next video. Take care.